Welcome to our deep dive into the world of bearings. Whether you're an engineering enthusiast or just curious, join us as we unravel the basics, explore different types, and discover how these engineering marvels keep our world turning. To start, let's journey back in time. Picture the heart of a wheel hub, the conventional journal bearing. In the early days of engineering applications, conventional bearings were commonly used to support rotating machinery. They were simple, functional, and a testament to early engineering technology. However, as the demand for higher speeds and heavier loads increased, the limitations of these conventional bearings began to surface. These bearings relied on sliding surfaces, which led to significant friction and heat generation, ultimately restricting their efficiency and causing wear and failure at higher operating speeds and loads. To address these challenges, the rolling bearing was invented as a groundbreaking solution. The rolling bearing was designed to reduce friction and enhance load carrying capacity by introducing rolling elements between the inner and outer rings. Imagine a simple mechanical setup consisting of two concentric rings, an outer ring and an inner ring. In the wheel hub example, the inner ring is mounted in a way that allows it to rotate around its center, while the outer ring remains fixed in place and does not rotate. Now, let's introduce a roller into the picture. This roller is a cylindrical object with a circular cross-section. It is snugly fit between the inner and outer ring. As the outer ring begins to rotate clockwise, it imparts a tangential velocity to the roller. This means that the surface of the roller in contact with the outer ring receives a certain speed in the opposite direction. This is due to the friction between the roller and the outer ring surface. Since the inner ring is stationary, one side of the roller remains in contact with it, both preventing any rotational motion and initiating the roller's roll along the interface between the outer and inner rings. This innovative design allowed for smoother motion and significantly lower friction, making it ideal for high-speed and heavy-duty applications. The credit for the invention of the rolling bearing goes to Philip Vaughan, a Welsh inventor who patented the first design in 1794. Since then, rolling bearings have revolutionized various industries, becoming an essential component in modern engineering machinery and equipment. Please note that it took us considerable time to create and make this video available for you. So if you find it helpful, please make sure to like it and subscribe to our channel. We will start with the most common type of bearing, the deep groove ball bearing. These bearings offer low friction, smooth operation, and an extended service life. A deep groove ball bearing consists of an outer ring, a set of steel balls, and a cage made from brass or steel to retain the balls. It also includes rivets to secure the cage ends and an inner ring. The inner and outer rings feature deep, raceway-shaped grooves that enable the bearing to accommodate both radial and axial loads. Before moving forward, let's clarify the types of loads a bearing is designed to handle. First, there's the radial load. This is an external force or load acting perpendicular to the bearing's axis of rotation. Next, we have the axial load. This is an external force or load operating parallel to the bearing's axis of rotation. Then comes the combined load. Bearings may occasionally encounter both radial and axial forces simultaneously, resulting in a combined load that incorporates elements from both directions. Lastly, we address the moment load. This particular load generates a bending moment around the bearing's axis and is typically encountered when the bearing deals with off-center or misaligned loads. As we progress, we will evaluate the load capacity of each bearing using this system, offering a more detailed understanding of how each bearing performs in these load case scenarios. To quantify the performance of each bearing type, we'll employ the templates shown here, assessing them based on the 4 primary bearing loads discussed earlier. The rating system ranges from 0 to 4 points or chevrons, where 0 indicates poor performance and 4 represents exemplary performance. Let's return to the deep groove ball bearing and start with its bearing load ratings. Deep groove ball bearings excel at handling moderate radial, axial, and combined loads. However, they aren't well suited for moment loads. Due to their proficiency in managing moderate loads, deep groove ball bearings are ideal for applications such as electric motors, fans and blowers, power tools, and household appliances. Next up are cylindrical bearings. They feature cylindrical rollers for their rolling elements, allowing them to handle high radial loads. The rollers are guided by the ribs of the inner or outer rings. Without ribs, either the inner or outer ring can move axially. This makes them suitable as free side bearings, accommodating shaft expansion. With ribbed configurations, the bearing can effectively carry a minor axial load between the end of the rollers and the ribs. Moreover, they come in both single and double row designs, offering a diverse range of configurations. Now, looking at the cylindrical bearings' load performance, they excel in radial loads, earning a rating of 3 chevrons. However, their standard setup isn't optimized for axial loads. Although adjustments can enhance its axial load capacity in its unmodified form, the cylindrical bearing is not ideal for either axial or combined loads. Furthermore, its ability to handle moment load is limited unless it's paired in opposing directions. Ultimately, these bearings shine in applications demanding heavy radial load, making them top choices for drive shaft bearings, rolling mills, and mining equipment. Tapered roller bearings consist of tapered rollers, a cage, and 2 tapered inner and outer races. Tapered roller bearings are designed so the inner-outer ring raceway and apex of the tapered rollers intersect at one point on the bearing center line. Their tapered design enables them to support both radial and axial loads effectively. Moreover, they provide smooth and efficient load distribution, reducing the risk of edge stresses and increasing the bearing's longevity and reliability. For bearing load performance, they earn 3 points or excellent for radial load handling and 4 points or exemplary rating for axial loads. They are also highly capable of managing combined loads, thus earning an excellent rating in that category. However, single tapered roller bearings aren't designed to effectively accommodate moment loads. Tapered roller bearings can withstand thrust forces generated during cornering or heavy loads, making them popular in automotive wheel hubs and gearboxes. Moving further down our list, we arrive at spherical roller bearings. These bearings stand out due to their ability to accommodate misalignment. They feature barrel-shaped rollers arranged in 2 rows in a spherical outer ring raceway. Such a design ensures that the barrel-shaped rollers, guided by the inclined raceways of the inner ring, can adjust or realign themselves freely along the concave outer ring raceway. Examining the bearing load performance chart for spherical bearings reveals their exemplary capability in managing radial loads, for which they earn top marks. While they can handle axial loads, they don't excel in this regard, garnering 2 points. Their excellent capability in managing combined loads earns them 3 points. Owing to their distinct design, they can also manage some moment loads. As highlighted, the advantages of spherical roller bearings enable them to accommodate heavy radial loads, misalignment between shaft and housing, exceptional resistance to shock and vibration. This makes them perfect for use in the railway industry's axle boxes, construction machinery, the oil and gas sector, and wind turbines. Next, we have needle roller bearings, which are highly valued for their compactness. These bearings are composed of needle-like cylindrical rollers housed within a thin outer ring. Notably, these rollers are supported by needles. Their streamlined design enables them to manage high radial loads despite their modest cross-sectional area. This design efficiency allows needle roller bearings to be effectively utilized in applications where space efficiency is a critical consideration. An analysis of their bearing load performance reveals excellent capabilities in managing radial loads. However, they are less suited for applications that are subjected to axial and combined loads. Regarding moment loads, substantial moments can cause uneven stress distribution within the bearing, potentially leading to premature failure. Beyond their compactness, needle roller bearings are distinguished by their robust load-carrying capacity and ability to minimize friction, making them an ideal choice for high-speed operations and precision machinery. Due to these characteristics, needle roller bearings are commonly used in internal combustion engines, motorcycles, aerospace applications, and robotics. We come across a type reminiscent of the deep groove bearing, but with an added enhancement, the angular contact bearing. While they share similarities with deep groove ball bearings, such as comprising a set of steel balls, a cage, and inner and outer rings, the angular contact bearings have a distinguishing feature. As highlighted in the animation, the inner and outer ring raceways are inclined relative to the bearing axis. These features, known as the shoulder edge and the relief edge, play distinct roles. The shoulder edge provides structural support and manages axial load, while the relief edge is instrumental in reducing stress concentrations that might arise at the shoulder edge. This configuration allows them to withstand both radial and axial loads simultaneously, with the contact angle determining the load capacity. Analyzing the bearing load performance chart for these bearings showcases their capability in handling radial loads, securing 2 points, and excel in managing both axial and combined loads, earning 3 points for each. Though not inherently designed for moment loads, their distinct design enables them to bear minor momentary loads. Angular contact bearings find frequent utility in pumps and compressors, vehicle steering systems, and medical equipment. Their ability to handle combined loads and high stiffness contribute to improved equipment performance and reliability. Next, we're showcasing a distinct type of bearing with exceptional attributes: the self-aligning bearings. Designed with 2 rows of balls or rollers and a spherical outer ring raceway, these bearings possess a distinctive feature. The rolling elements in one row don't precisely align with those in the opposite row, but are centered between the 2 opposing rolling elements. This special configuration in the bearing ensures that loads are evenly distributed between both rows, maximizing the bearing's load, carrying capacity, and minimizing wear. In situations of shaft misalignment or mounting errors, traditional bearings might face challenges, risking premature wear or failure. However, the self-aligning bearings with their staggered elements smoothly handle such issues, achieving uniform load distribution and maintaining smooth operation. While these bearings are predominantly designed to address misalignments, their load performance chart indicates a highly possible application scenario for radial loads where they earn 2 points, with their axial load slightly trailing their radial load rating and earning only 1 point. In combined loads, they score similarly. When it comes to moment loads, a single self-aligning bearing is not ideally suited to handle them, but can manage moderate moment loads. In conclusion, this specialized construction of rolling elements is a clever design feature that allows the bearing to accommodate and correct for misalignments, leading to increased operational efficiency, reduced wear, and extended bearing life. Their value becomes evident when we consider their frequent deployment in applications vulnerable to shaft deflection or alignment issues, such as conveyor systems, steel rolling mills, and agricultural equipment. Introducing the final type of bearing for our exploration: thrust bearings. These specialized bearings are meticulously designed to handle axial loads and consist of rolling elements, such as balls or rollers, sandwiched between 2 raceway rings. They ensure smooth and efficient axial movement, mitigating damage from excessive thrust forces and improving the overall performance and longevity of the machinery. An examination of the bearing load performance chart for thrust bearings highlights their outstanding capability in managing axial loads, earning them top marks. However, they aren't designed to handle radial loads, with the exception of thrust spherical roller bearings, which can manage minor radial loads. They also aren't equipped to handle combined loads, and, unsurprisingly, are not built to accommodate moment load. The benefits of thrust bearings include their ability to handle high axial loads and their compact design, which is invaluable in space-restricted applications. Thus, they find common use in turbochargers, vehicle clutches, aircraft engines, and HVAC systems. In our next video, we will present real-world examples of applications for each type of bearing we've discussed. Additionally, we will explore the load distribution for each bearing type within its specific application. Now, let's give you a quick preview of our upcoming video on bearing applications here. Thank you all for joining us on this exploration of bearing types. If you found this information valuable and enjoyed the video, please give it a thumbs up. Don't forget to subscribe to our channel for more insightful content. Until we meet again, keep learning and stay curious. Goodbye.